All right, this one's asking us to find both the radius of convergence and the interval of convergence. Although we do have some powers of n here, I don't know that the root test would work because that denominator, I don't know that we know what the limit of the nth root of n plus square root of n plus 1 is going to be. So let's go with our ratio test. So we're going to do a ratio here of the absolute value of these two, and bottom's just going to be our regular series. On top, we want the n plus 1 of this, so it would be negative 3 to the n plus 1, x to the n plus 1, and on bottom there we got the square root of n plus 1 plus the additional one that was already there. All right, so let's simplify now. When doing this here, we're going to let's separate this into negative 3 to the n times another negative 3. On here, let's do the same thing with our x to the n and times an additional x there. This is all going to be square root of n plus 1 would be n plus 2. Then let's also multiply by the reciprocal of that denominator. So this is going to be square root of n plus 1 here. And on the bottom we got this and this. So what's going to cancel here? We got these should cancel. These should cancel. And I think that's it. So what we are left with then for this one is limit as n goes to infinity. I'm going to take the absolute value of this now. Absolute value of negative 3 we're going to have in there. We're going to have the absolute value of x. We got this square root of n plus 1. And then on the bottom we get this square root of n plus 2. So I'm going to kind of put these together now, and we end up with limit as n goes to infinity of, this is just going to be 3x, or 3 times the square root of x, 3 times the absolute value of x, and then I'm going to put these two square roots together, so it'd be square root of n plus 1 over n plus 2. So what is the limit as we go to infinity of that going to equal? Well, the n plus 1 over n plus 2, they got the same power and coefficient here of 1, so that's just going to go to 1. So we would get that this is 3 times absolute value of x times square root of 1, which would just be 1. So it looks like we get that this just equals 3 absolute value of x. Okay, so when is that convergent with either ratio or root test? When that is less than 1. So what we end up with here is that 3 times absolute value of x is less than 1. If we divide both sides by 3 here, that means absolute value of x is less than 1/3. So our radius of convergence, which they asked us to find in this one, is 1/3. So our radius of convergence is 1/3. Now they also asked us to find what is the interval of convergence. For that, we know that x is going to be between 1/3 and negative 1/3. We need to know, though, at 1/3 and negative 1/3 whether to include those endpoints. So we want to check both those endpoints now by putting the value back into the original problem. So on this one, let's start with 1/3. If x equals 1/3, what does our series become? Well, our series then becomes that we still are going to have that negative 3 to the n. We're putting 1/3 in for the x value here, so it'd be that to the n all over square root of n plus 1. Well, if I combine these two together, they both have the same power, then that becomes, sorry, got to twice there. That's going to become negative 3 times 1/3 would be negative 1 to the n. Okay, so that's an alternating series, and that alternating series would be decreasing. Does it decrease towards 0? So what we want to do is see what is the limit as n goes to infinity of the non-alternating part. So does this equal 0? Absolutely, yeah, that's gonna, the bottom's going to infinity, and so that's gonna go to 0. So this 1/3, this endpoint is convergent by alternating series. So we do want to, over here, make sure we include 1/3. Now let's test the other one. We got to test the other endpoint. We want to test negative 1/3. So if we put that in the same way, we have this. Now if we combine together these two, that would end up being positive 1 to the n. And positive 1 to the n is just going to make this 1 to the n is just 1, so it's just 1 over square root n plus 1. Now to see if that one is converging or not, we would want to look at a similar series, which would be the series 1 over square root n, which is the same as 1 over n to the half. What do we know about that one? That one is divergent by p series. So if that one's divergent, then our one over here that is comparable should also be divergent. So our interval then would be the one we got right here. This would be our interval of convergence. And you can write it like that, or if you want, another acceptable way would be to write it as x in the interval negative 1/3 to 1/3, but make sure you include 1/3 like that, because that's that boundary was convergent. All right, let's have you pause the video and try one out on your own here, see if you can solve this one. All right, hopefully you've had a chance to try this one. Looks like our nth root one would be the best on this because we have a power of n here and we don't have any factorials. So if we do that nth root of the absolute value of this, we'd set it up like this. We'd have the nth root of n then. We'd have just x plus 2 absolute value of that, because the nth root and the power of n would cancel. Same with this one, the nth power would cancel, and then we would have the nth root of this term 3 here. We've seen from previous videos that this is going to 1. Anytime you got nth root of n, that goes to 1. This part I showed over here, if you do that limit, remember square root, or the nth root could also be written as 1 over n. And we know as we go to infinity that that's going to be 0. And so 3 to the 0 equals 1. So this whole thing's also going to go to 1. So that just leaves us with absolute value of x plus 2 over 3. So now we can figure out what our radius of convergence is, because in order for this to be convergent, it's going to have to be less than 1 by the root and ratio test. And so if we times by 3, that tells us that x plus 2 has to be less than 3. So because we have 3 as our value, our radius of convergence is 3. If we want to find our interval of convergence, we now know that x plus 2 should be between 3 and negative 3 here. And then if we minus 2 from everything, we're going to get that x is going to be between -5 and 1. Now, you do need to check those endpoints on this one, or hopefully you should have. It does turn out that both those endpoints are not included because they're divergent. So if we put 1 here in for where the x was, now we got 1 plus 2, which is the same as 3. Those 3 to the n's cancel, so it's the same as just this series, which diverges because it's going to get very big as we go to infinity. And if you put -5 in, that ends up being -3 to the n. We can split that up as -1 to the n and 3 to the n. Now those 3 to the n's cancel, so we're left with this alternating series here. If you check the part that is not alternating as we go to infinity, that's not going to 0, so this is a divergent endpoint as well. So both endpoints are divergent. That's why the interval of convergence just ends up being what we had right there. So depending on what they ask, interval or radius, be prepared to answer both. All right, let's look at this one. Find the radius of convergence and interval of convergence of this series. So they have this on top, this 1 times 3 times 5, dot, 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 that it's 2n plus 1. On the bottom, they have a factorial, and then x to the n. Well, factorial right away should clue us in that this one is going to be a ratio test. So let's set up a ratio test. We want our absolute value in there. Bottom we always know is going to be this series that we're given. I'm going to write the x to the n in here. And then on top, we have the same thing plus 1. So we've seen a few of these things before. This is going to become x plus 1 factorial. Our x here is going to be x to the n plus 1. What about our this thing? Because we haven't seen one of these before in an example. So what we're going to have here is that this is going to be the same thing plus 1. So we again want to put a plus 1 where we see the n there. So this is going to become 2n plus 1 plus 1. And we should have the same numbers all the way up to whatever that's going to be. So let's see how this one simplifies it. So we got limit, then goes to infinity. All our n stuff doesn't need the absolute value, but we do need to keep it around our x value here. So this is going to be written out here as all this stuff 1 times 3 times 5 all the way up. I'm going to simplify what we got written here. So if we distribute, that's going to be 2n plus 2. But we still have that plus additional 1, so it's going to end up being all the way up to 2n plus 3. We got our absolute value of x to the n plus 1 all over our n plus 1 factorial. I'm also at this point going to multiply by the reciprocal. So on top, we're going to end up with a n factorial. On bottom here, we're going to have, and I'm going to slide this over, factorial. We're going to have our absolute value of x to the n here. And we're also going to have this 1 times 3 times 5 all the way to 2n plus 1. Okay, so how do we simplify this? Well, we've seen before with some of this stuff how we can simplify here. So with our absolute value of x, we can do that as absolute value of x to the n times absolute value of x to the first power. On bottom here, n plus 1 can be written, factorial can be written as n plus 1 times n factorial. And we got this. So some of these things are going to cancel. That's going to cancel. That's going to cancel. But what about this business of 1 times 3 times 5 2n plus 1? Well, this series is going, it's all the numbers multiplied where it's going up by 2, starting at 1. So what would if we were to write this out on top, it'd be 1 times 3 times 5, all the way up to, now this is 2n plus 3. So the term before that would be 2 less. So if we subtracted 2 from that, that would be 2n plus 1. And then the next term would be the 2n plus 3. So all these terms leading up to that last one should cancel with everything down here. So now we're just left with the following stuff. The limit as n goes to infinity of, on top we got the 2n plus 3. We also got that absolute value of x. On bottom we get the n, just n plus 1, n plus 1. All right, so what's the limit of this going to be? Again, I'm going to disregard this absolute value of x right now and put that over here. Let's focus on this fraction part. As we go to infinity, what is that going to go to? Well, if we were to multiply this by 1 over n, we can see it pretty quickly here that we have 2 plus 3 over n, and here we got 1 plus 1 over n. All those two terms are going to go to 0, so that's going to go to 2. So we got 2 times the absolute value of x. So that's what we end up with there for our limit. So when is this going to be convergent? It's going to be convergent when that is less than 1, which, if we divide by 2, tells us that our radius of convergence is 1/2. Okay, so now for our interval, we know our interval of convergence is going to be between 1/2 and -1/2. We want to now check those endpoints. So if we put those endpoints back up into the original one, or put that value in, what do we get? So if we checked 1/2 here, this is going to be this thing leading up to 2n plus 1 over n factorial of 1/2 to the n. By geometric series, we know that this is going to go to, or that one, sorry, should be, so yeah, this geometric would tell us we're going to 0, but then we also have this other part over here. What is that going to be doing? Well, these numbers on top here, because we're skipping every other one here, is I'm pretty sure going to be bigger than that. And you can test that by, if you put a certain number in there, you can see that the numerator on this is bigger than what the denominator combined with this are going to be. So this is going to be divergent, and same with -1/2. If we put that in there, that alternating series will also end up being divergent. So we'd only want to, or would not include either of those two endpoints of this one. Would be the interval of convergence here. All right, one last one here. Let's have you again pause and try this one out on your own and see what you come up with. All right, hopefully I've had a chance to try it. We'll use the nth root one on this one because we got a power of n here. So if we do that, the top should just be absolute value. Make sure you get the absolute value in there of 2x minus 1. Nth root of this, we can kind of take some liberties here. We know if we just look at the main part of this, it would be nth root of n to the 4th, which could also be written like this. And we've seen that the nth root of n as we go to infinity is 1, so that's just 1 to the fourth or 1. Even if we did have some constant in here, like the plus 16, and let's say that n to the fourth ends up being like a 1 or something, so we get 17 to the nth root of 17. Remember, nth root can be written as 1 over n. As that goes to infinity, that's just going to be 17 to the 0 power, which also equals 1. So all that denominator will just end up being 1 there. So we end up with just the absolute value of 2x minus 1. For that to be convergent with root or ratio test, it needs to be less than 1. And so our radius of convergence here is 1. If we solve that now, putting it equal to both, or less than 1 and greater than negative 1, add 1 to both, and then divide by 2. Here's our interval. Now we should check the endpoints. If we plug in 1 over here, we get the series of just 1 to the n. Well, 1 to the n is just going to always be 1 here. That series is convergent by comparison to p series of 1 over n to the fourth. If we put 0 in there, we got negative 1 to the n. By alternating series test, that's decreasing to 0, so that is convergent as well. So we want to include both the endpoints in this one. So that should be our interval of convergence.